Hello and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind and step quietly into the vast, starlit corridors where endings become beginnings. Tonight, we're exploring galactic graveyards, places where stars have finished their brilliant lives and left behind monuments written in matter and light. If you enjoy these quiet journeys, a like and subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. There was a moment, roughly 11,000 years ago, when a star in the constellation Cassiopeia ended its life. The explosion released more energy in seconds than our sun will produce in its entire 10 billion year lifetime. Light from that death travelled across the galaxy at 186,000 miles per second, crossing the vast emptiness between stars, passing through clouds of gas and dust, journeying through darkness for millennia. Then, sometime in the 1600s, that light finally reached Earth. Someone might have looked up and noticed a new star where none had been before, brighter than anything else in that patch of sky, visible even through the haze of candles and hearth fires. Today, we call that remnant Cassiopeia A. It glows in X-rays, radio waves, and visible light, a delicate lacework of expanding gas still rushing outward from the explosion. When astronomers point their most sensitive instruments at it, they see filaments of oxygen, silicon, iron, elements forged in the star's core and scattered into space. The star itself is gone, collapsed into something almost incomprehensibly dense, a neutron star no wider than a city but containing more mass than the sun. What remains is not silence but transformation, not emptiness but an archive, a record written across light years of space. This is what happens when stars die. They do not simply vanish. They leave behind structures, remnants, ghosts of their former selves. And the galaxy is filled with them. Billions of stars have already reached the end of their lives, and their remains are scattered throughout the Milky Way like monuments in an ancient cemetery. Astronomers call these places galactic graveyards, not because they are sad or forgotten, but because they hold the memory of what once burned brightly. These graveyards are not empty. They pulse, they glow faintly, they bend space, and they shape the future of everything that comes after. The impossible part is not that stars die, it is that we can see their deaths written across the sky, preserved in light that travelled for thousands or millions of years to reach us. It is that their endings are not final, but are instead woven into the fabric of new beginnings. Every atom of carbon in your body, every molecule of oxygen in the air, every trace of iron in your blood was made inside a star, and released when that star died. You are, in the most literal sense, made of remnants. The graveyard is not somewhere distant. It is here, within you, around you, part of the same cosmic cycle that governs everything. When you look up at the night sky, you are not seeing only living stars. You are also seeing the afterglow of ancient explosions, the faint light of cooling embers, the invisible presence of objects so dense that light cannot escape them. The sky is a mixture of past and present, of life and death, of beginnings and endings all happening at once. And if you know where to look, if you have the instruments to listen carefully, you can hear the whispers of the graveyard speaking across time. This is where our journey begins, with the astonishing, verified fact that stars do not last forever, that their deaths are not erasures, but transformations, and that the remnants they leave behind are some of the most fascinating and important objects in the universe. Galactic graveyards are vast, scattered, and filled with secrets. They challenge our understanding of matter, energy, time, and space. They connect the distant past to the present moment, and they remind us that endings are never truly final, that every death in the cosmos carries within it the seeds of something new. So tonight, we will wander through these graveyards slowly, patiently, with curiosity and calm. We will explore what happens when stars exhaust their fuel, what remnants they leave behind, and what those remnants tell us about the universe. We will see how death and creation are inseparable, how silence and activity coexist, and how the graveyard is not a place of loss but a place of memory, persistence, and renewal. The The impossible beginning is this, that we are alive at all, made from the ashes of stars that died long before the sun was born. The Milky Way galaxy is old, not as old as the universe itself, but old enough that countless generations of stars have already lived and died within it. Astronomers estimate the galaxy formed roughly 13 billion years ago, not long after the universe began. In that time, it has grown, changed, and evolved. Stars have ignited, burned brightly, and faded. Gas clouds have collapsed, planets have formed, and entire stellar neighbourhoods have risen and fallen. The Milky Way is not a static structure, but a dynamic, living system where birth and death happen constantly, woven together in cycles that span billions of years. From Earth, the galaxy appears as a band of light stretching across the night sky, a soft glow made of billions of stars too distant to see individually. That glow is beautiful, but it hides complexity. Within the Milky Way are spiral arms where new stars are born, dense clusters where stars crowd together, and vast halos where ancient stars drift in relative isolation. There are bright nebulae glowing with the light of young stars, and dark clouds where light cannot penetrate. And scattered throughout, visible to the naked eye but detectable with instruments, are the remnants of stars that have already finished their lives. These remnants are what we call galactic graveyards. They are not confined to a single location. They are everywhere, woven into the structure of the galaxy itself. Some are clustered near the galactic centre, where stars are dense and interactions are frequent. Others are scattered in the spiral arms, left behind by recent explosions. Still others drift in the halo, ancient remnants from the galaxy's earliest days. The graveyard is not a place you can visit in the way you might visit a cemetery on Earth. It is distributed, diffuse, and intermingled with the living stars. Yet it is real, measurable, and vast. To understand where galactic graveyards began, we must go back to the galaxy's youth. In the earliest epochs, the Milky Way was smaller, less organised, and filled with gas that was almost entirely hydrogen and helium. These were the only elements available, the raw materials left over from the Big Bang. The first stars to form were massive, hot, and short-lived. They burned through their fuel quickly, perhaps in only a few million years, and then exploded as supernovae. Those explosions scattered heavier elements into space, enriching the gas clouds and making it possible for the next generation of stars to form with more complex chemistry. Over time, this process repeated. Each generation of stars added more heavy elements to the galaxy. Carbon, oxygen, nitrogen, silicon, iron, all the building blocks of rocky planets and living organisms were gradually produced and distributed. The galaxy became richer, more chemically diverse, and more capable of forming complex structures. But with each generation, the graveyard also grew. Every star that died left behind a remnant, whether a faint white dwarf, a dense neutron star, or an invisible black hole. These remnants accumulated, becoming part of the galaxy's hidden population. Today, the Milky Way contains an estimated 200 to 400 billion stars. But not all of them are alive in the sense of actively fusing hydrogen into helium. Many have already exhausted their fuel and transitioned into remnants. Some estimates suggest that billions of white dwarfs exist in the galaxy, most too faint to detect directly. Millions of neutron stars may be scattered throughout, many of them silent, no longer emitting the pulses that make them visible. And tens of millions of black holes could be hiding in the darkness, detectable only by their gravitational effects or when they interact with nearby matter. The setting for our exploration is therefore not a distant or exotic place. It is the galaxy we inhabit, the same galaxy visible on clear nights as a ribbon of light overhead. The graveyard is all around us, hidden in plain sight. When you look at the Milky Way, you are seeing both the living and the dead, the bright and the faint, the visible and the invisible. The galaxy is a mixture, a tapestry woven from countless lifetimes, and the remnants are as much a part of it as the shining stars. Understanding this setting helps us appreciate the scale of what we are exploring. Galactic graveyards are not rare or unusual. They are the natural outcome of stellar evolution, the inevitable result of the laws of physics playing out over billions of years. Every star will eventually join the graveyard, adding to the population of remnants. Our own sun will one day become a white dwarf, cooling quietly for billions of years. In that sense, the graveyard is not only a record of the past, but also a preview of the future. The Milky Way is also part of a larger structure. It belongs to a group of galaxies called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. All of these galaxies have their own graveyards, their own populations of remnants, and beyond the Local Group, billions of other galaxies fill the observable universe, each with its own history of stellar life and death. The graveyards we explore in the Milky Way are local examples of a universal phenomenon, patterns that repeat across the cosmos. This setting also grounds us in time. The remnants we observe today are not ancient in the sense of being unchanging. They are still evolving, still cooling, still interacting with their surroundings. A white dwarf formed 1 billion years ago is cooler now than when it first appeared. A neutron star that once pulsed brightly may have slowed down, its signals fading. A black hole that swallowed matter long ago may have grown slightly larger. The graveyard is not static. It is a living archive, constantly changing, constantly writing new chapters in the galaxy's history. So as we begin this journey, picture the Milky Way as it truly is. A vast disk of stars, gas, and dust, rotating slowly around a central black hole, spiral arms tracing patterns through space, regions of bright activity where new stars are born. And scattered throughout, in every direction, the quiet remnants of stars that have already completed their cycles. The setting is immense, but it is also intimate. We live within it, made from its materials, connected to its history. The galactic graveyard is not somewhere else. It is here, and it has been here for billions of years, shaping the galaxy and everything within it. For most of human history, stars were thought to be eternal. They rose and set with predictable regularity, marking the seasons and guiding travellers. Ancient astronomers mapped their positions, named constellations, and passed down stories that connected the sky to the Earth. But the idea that stars themselves could change, that they could be born, live, and die, was not obvious. It took centuries of observation, the invention of telescopes, and the development of new instruments before humanity began to notice the strange objects that populate the galactic graveyard. The first hints came in the form of novas and supernovas. These sudden appearances of bright stars in the sky were recorded by observers across cultures. In the year 1054, Chinese astronomers noted a guest star in the constellation Taurus, visible even during the day for weeks. European and Middle Eastern observers likely saw it too, though records are less detailed. That guest star was a supernova, the explosive death of a massive star. Today, we know it as the Crab Nebula, a glowing cloud of gas still expanding from that ancient blast. But at the time, it was simply mysterious, a star that appeared where none had been before. Over the centuries, more such events were recorded. In 1572, the Danish astronomer Tycho Brahe observed a supernova in Cassiopeia, an event so bright it challenged the prevailing belief that the heavens were unchanging. In 1604, Johannes Kepler observed another supernova. Visible for over a year, these observations suggested that the sky was not as permanent as it seemed, that something dramatic could happen among the stars. But without telescopes powerful enough to reveal the remnants left behind, the true nature of these events remained hidden. The invention of the telescope in the early 1600s opened new possibilities. Galileo turned his instruments skyward and saw moons orbiting Jupiter, phases of Venus, and countless stars invisible to the naked eye. As telescopes improved, astronomers began to notice faint, fuzzy objects scattered across the sky. Some were spiral galaxies, others were star clusters, and still others were nebulae, clouds of glowing gas. At first, these objects were catalogued without much understanding. Charles Messier, a French astronomer in the 1700s, compiled a list of over 100 such objects, intending to help comet hunters avoid confusing them with comets. But many of those objects would later be recognized as remnants of stellar death. In the 19th century, spectroscopy emerged as a powerful tool. By splitting light into its component colours, astronomers could identify the chemical elements present in distant objects. When applied to nebulae, spectroscopy revealed that some were made of glowing gas, while others were collections of stars. This distinction was crucial. It showed that not all fuzzy patches in the sky were the same, and it hinted at processes that could create glowing clouds of gas. But the connection to dying stars was not yet clear. The breakthrough came in the 20th century. Advances in physics, particularly the understanding of nuclear fusion and the structure of atoms, allowed scientists to develop theories about how stars work. They realized that stars are powered by fusion, converting hydrogen into helium and releasing energy in the process. This fusion sustains a star for billions of years, but eventually the hydrogen runs out. What happens next depends on the star's mass. For smaller stars like the Sun, the core contracts and the outer layers expand, creating a red giant. For massive stars, the process is more violent, leading to a supernova explosion. These theories predicted that dying stars should leave behind remnants. Small stars would shed their outer layers and leave behind dense cores called white dwarfs. Massive stars would explode and leave behind either neutron stars or black holes. These predictions were revolutionary, but they needed observational confirmation. And slowly, that confirmation arrived. In the 1930s, astronomers identified faint objects that matched the description of white dwarfs. Sirius B, the companion to the bright star Sirius, was one of the first. It was small, incredibly dense, and no longer fusing hydrogen. It was a remnant. Then, in 1967, came the discovery of pulsars. Jocelyn Bell Burnell, a graduate student at the time, noticed strange, regular pulses of radio waves coming from space. The signals were so precise that they were initially nicknamed LGM-1 for Little Green Men as a joke about extraterrestrial signals. But as more pulsars were found, the natural explanation became clear. These were neutron stars, the collapsed cores of massive stars, spinning rapidly and emitting beams of radiation. The discovery of pulsars confirmed that supernovae left behind dense remnants, objects so extreme that they stretched the limits of known physics. Black holes took longer to confirm. They had been predicted by Einstein's theory of general relativity, but detecting an object that emits no light is incredibly difficult. The breakthrough came through indirect evidence. Astronomers found stars orbiting invisible companions, their motions revealing the presence of massive, unseen objects. X-ray telescopes detected intense radiation from material falling into these objects, heating up and glowing before disappearing. By the late 20th century, the evidence for black holes was overwhelming. They existed, scattered throughout the galaxy, hidden but detectable through their gravitational influence. Each of these discoveries was a spark, a moment when the graveyard revealed a little more of itself. White dwarfs, neutron stars, black holes, all had been predicted by theory, but seeing them in reality was different. It confirmed that stars truly do die, that their remnants persist, and that the galaxy is filled with these objects. The graveyard was not a concept but a measurable reality, observable with the right instruments. What made these discoveries even more remarkable was what they implied. Stellar remnants were not just curiosities. They were clues to understanding the life cycles of stars, the processes that forge heavy elements, and the evolution of galaxies. Each remnant carried information about the star that created it, encoded in its properties. The mass, the composition, the motion, all told a story. The graveyard became a library, a place where astronomers could read the history of the galaxy written in the remnants of dead stars. The spark of mystery was this: that stars, which seemed eternal and unchanging, were actually temporary. They lived, they died, and they left behind traces that persisted for billions of years. And those traces were not hidden in some distant corner of the universe, but were scattered throughout the Milky Way, waiting to be found. The discovery of galactic graveyards was not a single moment, but a gradual unveiling. A process that continues today as astronomers find new remnants, map their distributions, and piece together the story they tell. When the first evidence of stellar death began to accumulate, The response from the scientific community was not immediate acceptance. Ideas that challenge deeply held beliefs rarely are. For centuries, the stars had been symbols of permanence. Philosophers, poets, and scientists alike saw them as fixed points in an ever-changing world. The notion that they could die, that they were subject to the same processes of birth and decay as everything else, required a fundamental shift in thinking. And shifts like that take time. The early observations of novas and supernovas were recorded with care, but their meaning was debated. Some observers saw them as new stars, created suddenly and then fading away. Others suggested they might be existing stars that had flared brightly for a time before returning to normal. The idea that a star could explode so violently that it left behind a remnant was not yet part of the conversation. Without a theory of stellar evolution, these events remained curiosities, interesting but not fully understood. When Tycho Brahe observed the supernova of 1572, he was struck by its implications. The prevailing cosmology of the time, based on Aristotle's ideas, held that the heavens were perfect and unchanging. Everything beyond the moon was eternal, while only the earth experienced change and decay. But here was clear evidence of change in the heavens. A star had appeared where none had been before, and it was bright enough to see, in daylight. Tycho's careful measurements showed that the object was far beyond the moon, in the realm of the fixed stars. This challenged the Aristotelian view directly. Yet even Tycho did not conclude that stars could die. He saw the event as unusual, a disruption of the expected order, but not as evidence of a life cycle. The conceptual framework for understanding stellar death simply did not exist yet. It would take centuries of accumulated observations and the development of physics before the pieces could come together. The awe was there, the sense that something profound had been witnessed, but the full meaning remained elusive. As telescopes improved and more objects were catalogued, astronomers encountered white dwarfs without recognizing them for what they were. Sirius B, discovered in the mid-1800s, was puzzling. It was a companion to Sirius, the brightest star in the night sky, but it was faint and difficult to observe. When its spectrum was finally measured in the early 1900s, astronomers were shocked. The spectrum indicated that it was extremely hot, much hotter than its faintness suggested. It was also incredibly dense. A star the size of Earth, but with a mass comparable to the Sun, defied all expectations. The initial response was disbelief. How could matter be compressed to such densities? The known laws of physics at the time did not account for it. Some scientists proposed alternative explanations, suggesting that the measurements were wrong or that some unknown process was at work. But as more white dwarfs were discovered, the evidence became undeniable. These objects were real, and they required new physics to explain. The development of quantum mechanics in the early 20th century provided that explanation. Electron degeneracy pressure, a quantum effect, could support a star, even after fusion had stopped. White dwarfs were not impossible, just extreme. The discovery of neutron stars met with similar skepticism. When the theoretical prediction was made in the 1930s, shortly after the discovery of the neutron itself, many physicists doubted whether such objects could exist. A star made almost entirely of neutrons, with densities far exceeding even white dwarfs, seemed absurd. But in 1967, when Jocelyn Bell Burnell detected the first pulsar, the skepticism began to crumble. The regularity of the pulses, their incredible precision, could only be explained by a rapidly spinning neutron star. The awe returned, mixed with disbelief that nature could produce something so strange. Black holes faced the longest period of resistance. Einstein himself was uncomfortable with the implications of his own theory. General relativity predicted that if enough mass collapsed into a small enough volume, space and time would be warped so severely that nothing, not even light, could escape. The idea seemed more like a mathematical curiosity than a physical reality. Many physicists believed that some unknown process would prevent such collapses from happening, but observations in the 1960s and 70s, particularly the detection of X-rays from binary systems, where matter spiraled into unseen companions, made the case for black holes compelling. By the late 20th century, the debate had largely shifted from whether black holes existed to how common they were. The awe and disbelief were not limited to scientists. When the public learned about these objects, the reaction was similar. White dwarfs, neutron stars, and black holes captured the imagination in ways that ordinary stars did not. They were extreme, mysterious, and slightly unsettling. They represented the limits of matter, the breakdown of familiar physics, and the strange possibilities hidden in the universe. Popular science writing and science fiction both embraced them, turning remnants into symbols of the unknown. But alongside the awe was a deeper, quieter realization. If stars could die, if the galaxy was filled with their remnants, then the universe was not static. It was dynamic, evolving, and filled with processes that connected past, present, and future. The graveyard was not an ending, but a continuation, a place where the cycle of matter and energy played out over cosmic time. This realization shifted how humanity saw itself in relation to the stars. We were not separate observers, but participants in the same processes, made from the same elements, subject to the same laws. The first response to the discovery of galactic graveyards was therefore a mixture of emotions: awe at the extremes of nature, disbelief at the implications, curiosity about what else might be hidden in the sky, and gradually, acceptance that the universe was stranger, more dynamic, and more interconnected than anyone had imagined. The remnants of dead stars were not anomalies, but essential parts of the cosmic story, and understanding them was essential to understanding everything. The universe seems to operate on a paradox. On one hand, the laws of physics are precise, consistent, and predictable. Stars form according to well-understood processes. They fuse hydrogen into helium, balancing gravity with the outward pressure of fusion. When the fuel runs out, they collapse or explode, leaving behind remnants that follow clear rules. Every step can be modelled, calculated, and tested. On the other hand, the remnants themselves, white dwarfs, neutron stars, and black holes, push the boundaries of those same laws into realms that feel almost mystical. They challenge intuition, defy ordinary experience, and reveal that the universe contains extremes far beyond anything we encounter in daily life. This contradiction between the predictable and the mysterious is at the heart of galactic graveyards. Science tells us what happens when stars die. Quantum mechanics explains how electron degeneracy pressure supports white dwarfs. Nuclear physics describes the formation of neutron stars. General relativity predicts the existence of black holes. These explanations are grounded in mathematics, tested by observation, and confirmed by experiment. Yet the objects themselves remain profoundly strange. A star compressed to the size of a city, a point of infinite density hidden behind an event horizon. Matter so dense that a teaspoon weighs billions of tons. These are not the kinds of things that fit comfortably into human understanding. Part of the contradiction lies in scale. The numbers involved in stellar death are so large or so small that they lose meaning. When we say a supernova releases as much energy in seconds as the sun will produce in 10 billion years, the statement is true, but it does not convey the reality. The mind cannot hold such comparisons. Similarly, when we describe a neutron star as having the mass of the sun compressed into a sphere 20 kilometers across, the description is accurate, but the actual density, the actual conditions, remain beyond imagination. Science gives us the framework, but mystery persists in the details. Another layer of the contradiction appears in the behavior of these remnants. White dwarfs are simple in concept, just the exposed cores of dead stars, cooling over billions of years, but their interiors are anything but simple. The matter is in a degenerate state, where quantum effects dominate. Electrons are packed so tightly that they resist further compression, not through ordinary pressure, but through the Pauli exclusion principle, a rule of quantum mechanics that forbids particles from occupying the same state. This is not the kind of pressure we feel when we squeeze something in our hands. It is a pressure that arises from the fundamental structure of reality, from the way particles behave at the smallest scales. Neutron stars amplify this strangeness. Their cores may contain exotic forms of matter, particles and states that cannot exist anywhere else in the universe. Hyperons, quark matter, or even stranger configurations might be present, crushed into existence by pressures so extreme that our laboratories cannot reproduce them. Scientists can model these possibilities, but without direct observation, which is impossible given the distances and the obscuring nature of the star's surface, certainty remains elusive. The neutron star is a laboratory of extreme physics, but it is one we can only probe indirectly, through the signals it emits and the effects it produces. Black holes deepen the contradiction further. General relativity describes them with precision. The mathematics is clear, the predictions are testable, and observations confirm that black holes exist. Yet at the same time, they embody the limits of our understanding. At the singularity, the point where all the mass is concentrated, the equations of general relativity break down. Density becomes infinite, space and time lose their usual meanings, and the laws of physics as we know them no longer apply. This is not a failure of science, but a signal that new physics is needed, a deeper theory that can reconcile general relativity with quantum mechanics. The event horizon adds another layer of mystery. It is not a physical surface, but a boundary in space-time, a point of no return. Anything that crosses it is lost to the outside universe, unable to send signals, unable to escape. Yet from the perspective of someone falling into a black hole, the crossing happens without drama. There is no wall, no barrier, just a smooth continuation of space. The contradiction is that the event horizon is both profoundly significant, marking the edge of what we can know, and utterly unremarkable, just another point in space from a different perspective. Science explains this duality through the geometry of space-time, but the explanation does not erase the strangeness. There is also a philosophical contradiction embedded in galactic graveyards. They are places of endings, the final states of stars that once burned brightly, yet they are also places of beginnings. The heavy elements scattered by supernovas seed new stars and planets. The remnants themselves shape the evolution of galaxies, influencing star formation, triggering collapses, and redistributing matter. Death and life are not separate but intertwined. Science describes the mechanisms, the ways in which matter cycles through different states. But the deeper mystery remains. Why is the universe structured this way? Why does death lead to creation? Why is destruction also generative? This contradiction does not undermine science. Instead, it highlights the richness of the universe, the fact that we can describe stellar death with precision, that we can predict the properties of remnants and test those predictions through observation, is a testament to the power of the scientific method. But the fact that the remnants themselves are so extreme, so far beyond ordinary experience, so filled with unanswered questions, shows that science is an ongoing process. There is always more to discover, always deeper layers of reality to uncover. For astronomers, this tension between science and mystery is part of what makes galactic graveyards so compelling. They are not just objects to study, but puzzles that push the boundaries of knowledge. Each new observation, whether it is the detection of gravitational waves from merging black holes or the measurement of a neutron star's mass, refines the theories and opens new questions. The graveyard is a place where science is most active, where the collision between what we know and what we do not know produces insights that reshape our understanding. For anyone looking at the night sky, the contradiction is quieter but still present. The stars seem stable, permanent, timeless, yet we know they are not. They are temporary, subject to the same processes of change and decay as everything else. The light we see left those stars years, decades, or centuries ago. Some of the stars we see may already be dead, their light still travelling toward us. The sky is a mixture of past and present, of the visible and the hidden. Science tells us this, but the mystery of seeing it, of feeling the weight of that knowledge while standing beneath the stars, remains. The contradiction between science and mystery in galactic graveyards is therefore not something to be resolved. It is something to be held, appreciated, and explored. The universe is both knowable and strange, both predictable and full of surprises. The remnants of dead stars embody that duality, and in studying them, we engage with both the power of science and the persistence of wonder. When astronomers first began to piece together the story of stellar death, the evidence was fragmentary, and the interpretations varied. White dwarfs had been observed, but their nature was debated. Neutron stars had been predicted, but many doubted they could exist. Black holes were mathematically possible, but whether nature would allow them was unclear. The graveyard was being mapped, but the map had many blank spaces, and different scientists filled those spaces with different ideas. Theories proliferated, each attempting to explain the strange objects being discovered, and in the process, minds divided. One of the earliest debates centered on white dwarfs. By the early 20th century, astronomers knew that some stars, like Sirius B, were incredibly dense. But how dense could matter actually become? Some scientists believed there must be a limit, a point beyond which compression was impossible. Others, following the new insights of quantum mechanics, proposed that electron degeneracy pressure could support a star even at densities far beyond anything encountered on Earth. The debate was resolved in the 1930s when the Indian astrophysicist Subramanian Chandrasekhar calculated the maximum mass a white dwarf could have and still remain stable. That limit, now known as the Chandrasekhar limit, is about 1.4 times the mass of the Sun. Chandrasekhar's work was groundbreaking, but it was not immediately embraced. When he presented his findings, the prominent astronomer Arthur Eddington dismissed them, arguing that nature would find some way to prevent such extreme collapses. Eddington was not alone in his skepticism. The idea that a star could collapse beyond the white dwarf stage, that it could become something even denser, seemed absurd to many. But Chandrasekhar's mathematics was sound, and as more observations accumulated, the resistance faded. The division between those who accepted the new physics and those who clung to older ideas eventually resolved in favour of the evidence. The prediction of neutron stars followed a similar pattern. In the 1930s, shortly after the discovery of the neutron, physicists Walter Baade and Fritz Zwicky proposed that supernovas might leave behind cores made entirely of neutrons. These neutron stars would be incredibly small, only about 20 kilometers across, but they would contain more mass than the Sun. The idea was radical, and many scientists doubted whether such objects could form or remain stable. For decades, neutron stars remained a theoretical curiosity, mentioned in papers but not taken seriously by most astronomers. The discovery of pulsars in 1967 changed everything. The regular pulses detected by Jocelyn Bell, Burnell and Anthony Hewish were so precise that they seemed artificial at first. But as more pulsars were found, the natural explanation became clear. These were neutron stars, spinning rapidly and emitting beams of radiation. The theory that had been ignored for decades was suddenly vindicated. Minds that had been divided reunited around the evidence. Neutron stars were real, and they were scattered throughout the galaxy, most of them invisible but detectable through their pulses. Black holes provoked the deepest divisions. Einstein's general relativity predicted that if enough mass collapsed into a small enough volume, the result would be a singularity surrounded by an event horizon. But Einstein himself was uncomfortable with this prediction. He wrote papers suggesting that some mechanism must prevent such collapses. Other physicists shared his discomfort. The idea of a region from which nothing, not even light, could escape seemed to violate intuition. It also raised troubling questions about the fate of information, a problem that persists today in the form of the black hole information paradox. The debate over black holes was not just about whether they existed, but about what they meant for physics. If singularities formed, did that indicate a failure of general relativity? If event horizons existed, what happened to the matter and information that fell in? Some scientists proposed modifications to general relativity that would prevent black holes from forming. Others suggested that quantum effects might intervene at the last moment, halting the collapse before a singularity appeared. These were not idle speculations, but serious attempts to reconcile theory with philosophical concerns about the nature of reality. Observations gradually tipped the balance. In the 1970s, astronomers detected X-rays coming from binary systems where matter spiraled into invisible companions. The properties of these systems, the masses, the radiation, the dynamics, matched the predictions for black holes. The clinching evidence came later, with the detection of gravitational waves from merging black holes in 2015 and the imaging of a black hole's event horizon in 2019. By then, the division had largely healed. Black holes were real, and the task shifted from proving their existence to understanding their properties. But even with acceptance, divisions remain. Scientists still debate what happens at the singularity, whether it represents a true infinity or a signal that new physics is needed. They argue about the information paradox, whether information is lost, preserved in the radiation, or encoded on the event horizon. They explore the possibility of exotic objects, like wormholes or naked singularities, that general relativity allows, but which may or may not exist in nature. The graveyard is understood in broad strokes, but the fine details still provoke disagreement. Another division emerged around the role of stellar remnants in galactic evolution. Some astronomers emphasized their passive nature, seeing them as endpoints, objects that no longer contribute to the life of the galaxy. Others argued for their active role, pointing to how supernova remnants trigger star formation, how black holes regulate galaxies through feedback, and how white dwarfs can reignite in certain circumstances. This debate was never as sharp as the debates over existence, but it shaped how scientists thought about the graveyard. Was it a cemetery, a place of stillness, or was it a workshop, still shaping the galaxy? Theoretical divisions also appeared in the study of neutron stars. What exactly happens inside them? Are they made purely of neutrons, or do more exotic particles exist in the core? Do they have solid crusts or liquid interiors? These questions cannot be answered by observation alone because we cannot see inside a neutron star. Models are built, predictions are made, and observations of mass and radius are used to constrain the possibilities. But different models give different answers, and the divisions persist. Each new measurement helps, but certainty remains elusive. The divisions among scientists are not failures but features of the process. Science advances through debate, through the clash of ideas, through the testing of hypotheses against evidence. The history of galactic graveyards is a history of theories, proposed, challenged, refined, and sometimes abandoned. Each division represented a moment when the evidence was insufficient, when multiple interpretations were possible, and when minds had to weigh probabilities and make judgments. Over time, as observations improved, many divisions resolved. But new questions always appeared, ensuring that the process continues. For those outside the scientific community, these divisions can be confusing. Why do scientists disagree if the evidence is clear? The answer is that evidence is rarely clear at first. Observations are noisy, instruments have limitations, and interpretations depend on assumptions. Scientists divide not because they are careless, but because they are careful, weighing possibilities, testing alternatives, and remaining open to being wrong. The graveyard has been mapped through this process, and the map is now detailed, but it is not complete. Divisions remain at the edges, where new discoveries are still being made and where the next generation of questions is being formed. The theories that emerge from these divisions have given us a coherent picture of stellar death. Small stars become white dwarfs. Massive stars explode and leave behind neutron stars or black holes. Remnants persist for billions of years, shaping the galaxy and seeding new generations of stars. This picture is supported by vast amounts of evidence, and it is accepted by the scientific community. But acceptance does not mean the end of inquiry. The graveyard still holds mysteries, and minds continue to divide over the details, driven by curiosity and the desire to understand the universe more deeply. Understanding galactic graveyards required more than observation. It required pursuit, the active effort to find remnants, to measure their properties, and to piece together their stories. Astronomers could not simply wait for remnants to reveal themselves. Most are faint, hidden, or invisible in ordinary light. They had to be hunted, using specialized instruments, clever techniques, and decades of patient work. The investigation of the graveyard has been one of the great detective stories of astronomy, a pursuit that continues today with ever more sophisticated tools. The hunt for white dwarfs began with visual surveys. Astronomers scanned photographic plates, looking for faint stars that appeared blue or white, since hot white dwarfs emit most of their light at short wavelengths. But white dwarfs are dim, especially the older ones, and distinguishing them from ordinary stars required careful analysis of their spectra. Over time, catalogues were built, listing hundreds and then thousands of white dwarfs. Each discovery added a data point, helping astronomers understand the population, their temperatures, their masses, and their ages. Modern surveys have automated this process. Telescopes equipped with digital cameras scan vast areas of the sky, measuring the brightness and colour of millions of stars. Computer algorithms sift through the data, flagging objects that match the expected properties of white dwarfs. Follow-up observations confirm the candidates, and slowly the census grows. Today, astronomers have identified tens of thousands of white dwarfs, enough to study their distribution across the galaxy and to trace the history of star formation. Neutron stars presented a different challenge. Unlike white dwarfs, they do not emit much visible light. Their surfaces are small and hot, but they are also distant, making them difficult to detect directly. The breakthrough came with radio astronomy. Pulsars, the neutron stars that emit beams of radio waves, were discovered by accident when Jocelyn Bell Burnell noticed regular pulses in her data. Once the first pulsar was confirmed, the hunt began in earnest. Radio telescopes were turned skyward, scanning for similar signals. Over the following decades, thousands of pulsars were found, each one a neutron star revealing itself through its pulses. But not all neutron stars pulse. Some have magnetic fields too weak to produce beams. Others are oriented so that their beams do not sweep across Earth. These silent neutron stars are much harder to find. Astronomers look for them in other ways, searching for faint X-ray emissions from their hot surfaces or for gravitational effects on nearby stars. The effort is painstaking, but it is necessary to understand the full population. Each detection adds to the picture, showing that neutron stars are far more common than pulsars alone suggest. Black holes are the most elusive remnants. They emit no light, and their small size makes them invisible unless they interact with their surroundings. The pursuit of black holes has therefore relied on indirect evidence. Astronomers search for binary systems where a visible star orbits an unseen companion. By measuring the orbit, they can calculate the mass of the companion. If it exceeds the maximum mass for a neutron star, about 3 times the mass of the Sun, the companion must be a black hole. Dozens of such systems have been identified, providing strong evidence for stellar mass black holes. X-ray astronomy has been another key tool. When matter falls into a black hole, it heats up and emits X-rays before disappearing. Telescopes in space, above the Earth's atmosphere, can detect these X-rays and trace them back to their sources. Many of the best-studied black holes were found this way, through the glow of matter spiraling into them. The pursuit shifted from finding black holes to understanding their properties, measuring their masses, their spins, and their effects on surrounding material. Gravitational wave astronomy opened a new frontier. In 2015, the LIGO detectors captured ripples in space-time produced by 2 black holes merging. This was the first direct detection of gravitational waves and the first confirmation that black holes could merge. Since then, dozens of mergers have been detected, involving black holes and neutron stars. Each detection is a discovery, revealing not just the existence of these objects, but their masses, their distances, and the dynamics of their collisions. The pursuit of remnants has moved beyond light into the realm of space-time itself. The investigation of supernova remnants has followed a different path. These glowing clouds of gas are visible across the electromagnetic spectrum, from radio waves to gamma rays. Astronomers map their structures, measure their expansion rates, and analyze their compositions. Each remnant is a snapshot of a stellar explosion, frozen in time but still evolving. By studying many remnants at different ages, astronomers can trace the life cycle of these structures, from the initial blast to the eventual dispersal into the interstellar medium. Infrared astronomy has revealed hidden details. Dust in supernova remnants absorbs visible light but glows in the infrared. Telescopes like Spitzer and Herschel have mapped this emission, showing the distribution of dust and the presence of molecules. These observations reveal that remnants are not just hot gas, but complex environments where new materials are forming. The pursuit of understanding extends to chemistry. to the processes that create the building blocks of planets and life. The investigation has also moved beyond individual objects to populations. Astronomers now conduct large-scale surveys, counting remnants in different regions of the galaxy and comparing their numbers to theoretical predictions. They study the distribution of white dwarfs to understand the history of the Milky Way. They map the locations of pulsars to trace the structure of spiral arms. They estimate the number of black holes to constrain models of stellar evolution. The graveyard is no longer just a collection of objects, but a data set, a source of information about the galaxy as a whole. Computational models play a crucial role. Supercomputers simulate the deaths of stars, predicting what remnants should form and what properties they should have. These simulations are compared to observations, and discrepancies drive refinements. The pursuit is iterative, a back and forth between theory and observation, each informing the other. The graveyard is being mapped not just through telescopes, but through calculations. Through the effort to understand the physics that governs stellar death. The pursuit continues because the graveyard is vast, and many remnants remain undiscovered. Fainter white dwarfs, silent neutron stars, isolated black holes, all are still out there, waiting to be found. Each new generation of telescopes, each improvement in sensitivity, reveals more. The James Webb Space Telescope, the upcoming Extremely Large Telescope, and next-generation gravitational wave detectors will push the investigation further. The graveyard will continue to yield its secrets, but only to those who pursue them with patience, skill, and curiosity. The investigation of galactic graveyards is not built on grand visions or sweeping narratives. It is built on data, on the painstaking collection of clues and fragments that, when assembled, reveal the nature of stellar remnants. Every spectrum, every light curve, every timing measurement is a piece of evidence. Alone, these pieces might seem insignificant, but together they form a coherent picture of what happens when stars die and what remnants they leave behind. The data is where theory meets reality, where predictions are tested, and where the graveyard becomes tangible. Spectra are among the most important clues. When light from a star or remnant is split into its component colours, it produces a spectrum, a pattern of bright and dark lines that reveal the presence of specific elements. Each element absorbs or emits light at characteristic wavelengths, creating a unique fingerprint. By analysing spectra, astronomers can determine what a remnant is made of, how hot it is, and whether it is moving toward or away from us. White dwarfs, for instance, often show spectra dominated by hydrogen or helium, with occasional traces of heavier elements. These traces are clues about the star's past, about the fusion processes that occurred in its core. Light curves provide another layer of information. A light curve is a graph showing how the brightness of an object changes over time. For some remnants, the light is steady, but for others, it varies. Pulsars produce rapid, regular pulses, creating light curves with sharp peaks. Binary systems where a white dwarf accretes matter from a companion can show sudden brightening, called novae, followed by gradual fading. These variations are not random. They follow patterns determined by physics, and by studying the patterns, astronomers can infer the properties of the remnants. Timing measurements are crucial for pulsars. The pulses arrive with extraordinary regularity, and by measuring the intervals between them, astronomers can track the pulsar's rotation. Over time, most pulsars slow down as they lose energy, and the rate of slowing reveals information about their magnetic fields and ages. Some pulsars, however, show sudden changes in their rotation rates, called glitches, which provide clues about their internal structure. Timing data is so precise that it can detect effects of general relativity, such as the orbital decay of binary pulsars due to gravitational wave emission. X-ray observations reveal remnants that are otherwise invisible. Neutron stars, for example, are hot enough that their surfaces emit X-rays. By detecting these emissions, astronomers can locate neutron stars even when they are not pulsing. Accreting black holes and neutron stars also emit X-rays as matter spirals into them. Heating up to millions of degrees, the intensity and variability of the X-rays provide clues about the remnant's mass, spin, and the rate at which it is consuming material. X-ray data has been essential for identifying black hole candidates in binary systems. Gravitational wave data is the newest type of evidence. When two black holes or neutron stars merge, they produce ripples in space-time that travel outward at the speed of light. Detectors like LIGO and Virgo measure these ripples, capturing the signature of the collision. The waveform, the shape of the signal over time, encodes information about the masses and spins of the merging objects. By analysing the waveform, astronomers can determine whether the objects were black holes or neutron stars, how far away the merger occurred, and how the event unfolded. Gravitational wave data has opened a new window into the graveyard, revealing events that produce no light but which shake the fabric of space. Imaging provides visual clues. Supernova remnants, for example, can be photographed in different wavelengths, revealing their structures. Filaments of glowing gas, shells of expanding material, and central neutron stars all appear in images, each offering insights. The Hubble Space Telescope and other observatories have captured stunning images of remnants like the Crab Nebula, Cassiopeia A, and the Veil Nebula. These images are not just beautiful, they are scientific tools. By measuring the size and shape of remnants, astronomers can calculate their ages and the energy of the explosions that created them. Parallax measurements help determine distances. By observing a star or remnant from different positions in Earth's orbit, astronomers can measure the tiny apparent shift in its position against the background. This parallax allows them to calculate the distance, which is essential for determining other properties like luminosity and size. The Gaia satellite has measured parallaxes for over 1 billion stars, including many white dwarfs, providing a detailed three-dimensional map of the Milky Way's stellar population. Proper motion data tracks how remnants move across the sky. Some neutron stars, for instance, have high velocities moving rapidly through the galaxy. These velocities are clues about the supernova that created them, suggesting that the explosion was asymmetric and gave the neutron star a kick. By tracing the motion backward, astronomers can sometimes identify where the star formed, connecting the remnant to its birthplace. Chemical abundances are fragments of information encoded in spectra. When a supernova explodes, it scatters elements into space, and the proportions of those elements depend on the mass and type of the star. By measuring the abundances in supernova remnants, astronomers can reconstruct the fusion processes that occurred before the explosion. Oxygen, silicon, and iron are particularly informative. Their ratios reveal whether the star fused elements all the way to its core or whether the explosion was triggered by different mechanisms. Polarization measurements add another dimension. Light can be polarized, meaning its waves vibrate in a particular direction. Magnetic fields can cause polarization, and by measuring it, astronomers can map the magnetic fields around remnants. Pulsars, for example, often produce polarized radio waves, and the polarization changes as the beam sweeps across Earth. These changes provide clues about the structure of the magnetic field and the geometry of the emission region. All of this data, spectra, light curves, timing, X-rays, gravitational waves, images, parallaxes, proper motions, abundances, and polarization is collected, archived, and analyzed. Astronomers use sophisticated software to process the data, searching for patterns, testing models, and refining theories. The data is public, shared among researchers worldwide, allowing multiple teams to study the same remnants and verify each other's results. This openness ensures that the conclusions drawn from the data are robust and reliable. The data also accumulates over time. Objects observed decades ago are observed again with better instruments, and the comparisons reveal changes. White dwarfs cool, pulsars slow down, supernova remnants expand. By tracking these changes, astronomers can test predictions and refine models. The graveyard is not static, and the data captures its slow evolution. What makes the data powerful is its diversity. No single piece of evidence is definitive, but together the fragments build a coherent picture. A white dwarf spectrum tells us its temperature. Its parallax tells us its distance. Its luminosity tells us its size, and its mass tells us its history. Each clue depends on the others, and the picture emerges from the interplay. The graveyard reveals itself not in a single flash of insight, but in the gradual accumulation of evidence, the patient assembly of clues into knowledge. As astronomers gathered data and refined their theories, a deeper mystery began to emerge from the study of galactic graveyards. It was not just that stars died and left behind remnants, it was that those remnants played an essential role in the life of the galaxy itself. The graveyard was not a passive collection of dead stars, but an active participant in cosmic evolution. This realization shifted the entire perspective. What had seemed like endings were also beginnings. What had seemed like silence was also creation. The hidden truth was that death and life in the galaxy were inseparable, woven together in cycles that stretched across billions of years. The first hint of this deeper mystery came from studying the chemical composition of stars. Astronomers noticed that different generations of stars had different abundances of heavy elements. The oldest stars, found in globular clusters and the galactic halo, contained very little carbon, oxygen, or iron. Younger stars, like the Sun, contained much more. This pattern suggested that the galaxy had been gradually enriched over time, and the source of that enrichment was clear. Dying stars. When massive stars exploded as supernovae, they scattered heavy elements into space. When smaller stars shed their outer layers as planetary nebulae, they added carbon and nitrogen. Each generation of stars built on the remnants of the previous one. This realization transformed how scientists thought about stellar death. It was not just an ending, but a gift to the future. The carbon in living organisms, the oxygen in the atmosphere, the iron in Earth's core, all came from stars that died billions of years ago. Without those deaths, without the scattering of elements, planets like Earth could not exist. Life itself depended on the graveyard. This was the hidden truth, that the remnants were not separate from life but essential to it. The galaxy recycled its material, and the graveyard was the mechanism of that recycling. But the mystery deepened further. Astronomers began to study star formation and noticed that new stars often formed in regions near supernova remnants. The shock waves from explosions compressed nearby gas clouds, triggering their collapse. In this way, the death of one star could spark the birth of hundreds or thousands of others. The graveyard was not only a source of raw materials, but also a catalyst for creation. The cycle was more intricate than anyone had imagined. Death led to enrichment led to new stars, and new stars led eventually to more deaths, continuing the cycle. The role of black holes added another layer. Supermassive black holes at the centers of galaxies were found to regulate star formation. When they accreted matter, they released enormous amounts of energy, heating the surrounding gas and preventing it from collapsing into stars. This feedback could quench star formation in the central regions, shaping the evolution of the entire galaxy. Black holes, the ultimate remnants, were not passive endpoints but active agents, influencing the galaxy on the largest scales. The hidden truth was that even the most extreme remnants played roles that astronomers were only beginning to understand. Neutron stars revealed their own surprises. The detection of neutron star mergers through gravitational waves showed that these events produced heavy elements like gold, platinum, and uranium. These elements, rare and valuable on Earth, owed their existence to the collisions of stellar remnants. The galaxy's chemical complexity was not just a product of supernovae, but also of mergers, of the violent unions of dead stars. The graveyard was a workshop, forging elements that could not be made any other way. White dwarfs, too, had hidden roles. In binary systems, they could accrete matter from companions and occasionally reignite in thermonuclear explosions called Type Ia supernovae. These explosions were so consistent in brightness that they became tools for measuring cosmic distances. They revealed that the universe's expansion was accelerating, a discovery that led to the identification of dark energy. White dwarfs, the quiet remnants of ordinary stars, turned out to be keys to understanding the fate of the entire cosmos. The deeper mystery also touched on the origin of the heaviest elements. Supernovae could produce elements up to a certain point, but beyond that, the conditions were not quite right. Neutron star mergers provided the missing piece. When two neutron stars collided, the temperatures and densities were extreme enough to create elements all the way to the end of the periodic table. Observations confirmed this when astronomers detected the signature of heavy elements in the light from a neutron star merger in 2017. The graveyard was not just a repository but a factory, producing the full diversity of matter. This realization raised new questions. How many neutron star mergers had occurred in the galaxy's history? How much of the heavy elements came from supernovae versus mergers? How did the timing of stellar deaths influence the evolution of the galaxy? Each answer led to more questions, deepening the mystery. The graveyard was not a solved problem but an ongoing puzzle, with new pieces constantly being discovered. The hidden truth also extended to the structure of the galaxy. Simulations showed that the distribution of dark matter, the invisible substance that makes up most of the galaxy's mass, was influenced by the formation and movement of stellar remnants. Black holes, in particular, could sink toward the galactic center over time, affecting the density and shape of the dark matter halo. The graveyard was not separate from the larger structure, but embedded in it, shaping and being shaped by the galaxy as a whole. Even the future of the galaxy was tied to the graveyard. As more stars died, the supply of gas available for new star formation dwindled. Eventually, the Milky Way would exhaust its fuel, and star formation would cease. The galaxy would be left with only remnants, slowly fading over trillions of years. But before that, the Milky Way will merge with the Andromeda Galaxy, a collision that will trigger a burst of star formation, followed by a long decline. The graveyard of the future will be larger, more diffuse, and ultimately silent, but it will still be a product of the same cycles that operate today. The deeper mystery is that the graveyard is not an afterthought but a central feature of galactic life. It is where matter is processed, where elements are created, where energy is redistributed. It is where the past feeds the future, where endings become beginnings. The hidden truth is that we live within the graveyard, surrounded by its products, made from its materials, shaped by its cycles. The galaxy is not a machine with separate parts, but an interconnected system, where life and death are two aspects of the same process. Understanding the graveyard is understanding the galaxy itself. There comes a moment in the study of any great mystery when the accumulation of evidence, the weight of observation, and the clarity of theory converge into a shift in understanding. For galactic graveyards, that turning point came when astronomers realized that stellar death was not an anomaly but a necessity. It was not something to be explained away or minimized, but something central to the story of the universe. This paradigm shift changed everything. It reframed the graveyard from a place of endings into a place of transformation, from a collection of remnants into an engine of creation. The shift did not happen all at once. It emerged gradually as different lines of evidence converged. The discovery that heavy elements came from dying stars was one piece. The realization that supernova shock waves triggered star formation was another. The detection of neutron star mergers producing gold and platinum added a third. Each discovery on its own was significant, but together they painted a picture that was impossible to ignore. The graveyard was not peripheral to the galaxy's life, but essential to it. Without stellar death, there would be no chemical diversity, no rocky planets, no life. This realization challenged older ways of thinking. For much of human history, death had been seen as an ending, a cessation of activity, a loss. To apply that same concept to stars seemed natural. A star dies, it stops shining, and what remains is inert. But the evidence showed otherwise. What remained was active, transformative, and generative. A white dwarf might be cooling, but it was still a source of heat for billions of years. A neutron star might be silent, but it still shaped space with its gravity. A black hole might be invisible, but it still influenced everything around it. The remnants were not dead in the way that word implied. They were transformed, continuing to participate in the galaxy's evolution. The paradigm shift also changed how astronomers thought about time. Stellar life cycles operate on scales of millions to billions of years. A single human lifetime is far too short to see a star evolve. But by studying populations of stars at different stages, astronomers could piece together the sequence. Young stars in the Orion Nebula, middle-aged stars like the Sun, aging red giants, and ancient white dwarfs all coexisted in the galaxy. The graveyard was not something that would happen in the distant future. It was happening now, continuously, as stars of all ages moved through their cycles. Time in the galaxy was not linear but cyclical, with each cycle feeding the next. This shift in perspective had practical consequences. It meant that understanding the graveyard was not just an academic exercise, but a key to understanding the galaxy's past and future. By studying white dwarfs, astronomers could estimate the age of the galaxy, since the coolest white dwarfs were the oldest. By studying supernova remnants, they could trace the history of star formation, seeing where and when bursts of activity occurred. By studying neutron stars and black holes, they could probe the extreme physics that governed the universe's most violent events. The graveyard became a tool, a way of reading the galaxy's history written in the remnants of dead stars. The turning point also had philosophical dimensions. It challenged the idea of permanence. If even stars, which seemed eternal, could die, then nothing in the universe was truly permanent. Everything was temporary, subject to change, part of larger cycles. But this impermanence was not tragic, it was generative. The atoms of one star became the seeds of the next. The energy released in death powered new creation. The cycles ensured that the universe was not static but dynamic, always evolving, always creating new forms. The graveyard embodied this truth, showing that endings and beginnings were inseparable. For the public, this paradigm shift was captured in a single phrase: "We are made of stardust." It became a way of expressing the connection between stellar death and human existence. The phrase was poetic, but it was also scientifically accurate. Every atom heavier than helium in our bodies came from stars that died before the sun was born. The calcium in bones, the iron in blood, the oxygen in every breath. All were products of the graveyard. This realization connected the abstract concepts of astrophysics to the lived reality of being human. It made the graveyard personal, immediate, and profound. The shift also influenced how scientists approached new discoveries. Instead of seeing remnants as endpoints, they began to see them as participants in ongoing processes. When neutron star mergers were detected, the question was not just whether they produced gravitational waves, but what elements they created and how those elements spread through the galaxy. When white dwarfs were studied, the question was not just how they cooled, but what role they played in galactic ecology. The graveyard was no longer a static subject, but a dynamic one, full of interactions, feedback loops, and connections to the larger cosmos. This turning point was reinforced by computational models. Simulations of galaxy evolution began to include stellar death as a central process. They showed how supernova feedback regulated star formation, how black holes shaped galactic cores, and how the chemical enrichment changed over time. The models confirmed what observations suggested: that the graveyard was not separate from the galaxy's life, but integral to it. The paradigm shift was complete. Stellar death was no longer an ending, but a transformation, no longer a loss, but a contribution, no longer separate from creation, but inseparable from it. Every star that dies sends ripples through the galaxy. These ripples are not metaphorical, but physical, measurable, and profound. When a massive star explodes as a supernova, the blast wave races outward at thousands of kilometers per second, ploughing through the surrounding gas. When a white dwarf sheds its outer layers, those layers expand into space, carrying material and energy away from the core. When neutron stars merge, they release bursts of radiation and heavy elements that spread across light years. Each death creates consequences that propagate outward, affecting the environment, shaping the future, and leaving marks that persist for millions of years. The most immediate consequence is the shock wave. When a supernova explodes, the energy released in the first seconds is staggering. The shock wave expands outward, sweeping up the surrounding gas and compressing it. This compression heats the gas to millions of degrees, causing it to glow in X-rays. The shock wave also accelerates particles to enormous speeds, creating cosmic rays that travel through the galaxy for millions of years. These cosmic rays carry energy far from the explosion, depositing it in distant regions and influencing the chemistry of the interstellar medium. The shock wave also triggers star formation. When it encounters a dense cloud of gas, it compresses the cloud, causing parts of it to collapse under their own gravity. Within a few million years, new stars can ignite in these compressed regions. In this way, the death of one massive star can lead directly to the birth of hundreds or thousands of new ones. Astronomers have observed this process in action, finding young star clusters near supernova remnants, their ages matching the time since the explosion. The consequence is not just destruction but creation, the immediate ripple sparking new cycles of life. Another consequence is chemical enrichment. Supernovae scatter heavy elements into the interstellar medium, mixing them with the existing gas. This enrichment changes the properties of the gas, making it more capable of cooling and collapsing into stars. It also seeds the raw materials for planets. Without this process, the galaxy would contain only hydrogen and helium, and rocky planets like Earth could not form. The immediate ripple of a single supernova might enrich a region hundreds of light years across, affecting countless future systems. The energy released by dying stars also heats the interstellar medium. Supernovae, stellar winds from massive stars, and the radiation from hot white dwarfs all contribute to maintaining a warm, diffuse phase of gas between the stars. This hot gas fills much of the galaxy's volume and plays a role in regulating star formation. If too much gas is cold and dense, star formation proceeds rapidly, consuming the available material. But the energy from stellar deaths keeps much of the gas warm, slowing the process and allowing star formation to continue over billions of years. The consequence is a kind of self-regulation, where the deaths of stars moderate the births of their successors. Black holes and neutron stars also create immediate ripples. When a black hole forms, it can accrete nearby material, pulling it into a swirling disk. The material heats up as it spirals inward, emitting X-rays and sometimes jets of particles that shoot outward at nearly the speed of light. These jets can extend for thousands of light years, carving out cavities in the surrounding gas and redistributing energy on galactic scales. The consequence is that a single black hole, though small, can influence regions vastly larger than itself. Neutron star mergers produce their own unique consequences. When two neutron stars collide, they release not only gravitational waves but also a burst of gamma rays and a glow of light called a kilonova. The kilonova comes from the decay of heavy elements created in the merger, elements like gold, platinum, and uranium. These elements are ejected into space at high speeds, enriching the surrounding gas. A single merger can produce several Earth masses of gold, scattering it across light years. The immediate ripple is the seeding of rare, heavy elements, contributing to the chemical diversity of the galaxy. The consequences extend beyond physics to the structure of the galaxy itself. Supernova explosions and stellar winds drive turbulence in the fair interstellar medium, stirring the gas and preventing it from settling into a smooth distribution. This turbulence creates complex structures, filaments, bubbles, and cavities that can be seen in radio and infrared maps of the galaxy. The turbulence also affects magnetic fields, amplifying them and shaping their structure. The immediate ripple of stellar death is therefore not just a local event, but a force that shapes the large-scale environment. There are also social consequences, in the sense of how stellar deaths affect the stellar population. Each supernova removes a massive star from the galaxy, one that might have lived only a few million years, but it leaves behind a remnant, a neutron star or black hole that can persist for billions of years. The population of the galaxy shifts over time, with fewer massive stars and more remnants. This shift changes the overall brightness of the galaxy, its colour, and its ability to form new stars. The immediate ripple of each death accumulates, shaping the galaxy's long-term evolution. For planets orbiting nearby stars, the consequences can be dramatic. A supernova within a few tens of light years could bathe a planet in radiation, stripping away its atmosphere or triggering mass extinctions. Earth has experienced several mass extinctions in its history. and some scientists have speculated that nearby supernovae might have been responsible. The evidence is indirect, traces of certain isotopes in rock layers that could have come from cosmic rays, but the possibility is real. The immediate ripple of a stellar death can reach across light years, affecting worlds that seem distant and safe. The consequences are also temporal. The material ejected by dying stars does not stay in one place. It expands, mixes with other gas, and gradually disperses. Over millions of years, the remnant of a supernova blends into the background, becoming indistinguishable from the general interstellar medium. But the elements it carried persist, incorporated into new stars and planets. The immediate ripple fades, but its effects endure. The galaxy today is a mixture of countless such ripples, layers upon layers of consequences from billions of stellar deaths. Understanding these consequences helps astronomers predict the future. As the Milky Way ages, more stars will die, and more remnants will accumulate. The immediate ripples will continue, but the overall rate of star formation will decline as gas is consumed or ejected. Eventually, the galaxy will enter a quieter phase, with fewer explosions and fewer new stars. But that is billions of years away. For now, the immediate ripples continue, each death shaping the galaxy in small but significant ways. The immediate consequence of stellar death is therefore not a single event but a cascade of effects. Energy spreads, matter enriches, shocks compress, and creation follows destruction. The ripple moves outward, carrying with it the influence of the star that was, touching everything in its path, and leaving behind a changed galaxy. The graveyard is not static. It is dynamic, constantly sending out ripples that propagate through space and time, shaping the present and the future. If the immediate ripples of stellar death are like waves spreading across water, then the long-term impacts are like the currents those waves create, persisting long after the initial disturbance has faded. The death of a star is not just a momentary event, but the beginning of a process that echoes through time, shaping the galaxy for millions and billions of years. These echoes are written into the chemical composition of stars, the distribution of gas, the structure of galaxies, and even the emergence of life itself. The impact of galactic graveyards extends far beyond the remnants themselves, reaching into every corner of cosmic history. One of the most profound impacts is the chemical evolution of the galaxy. When the Milky Way first formed, it contained almost no elements heavier than helium. The first stars were made of primordial gas, simple and pure. But as those stars lived and died, they enriched the interstellar medium with heavier elements. Carbon, oxygen, nitrogen, silicon, iron, all were produced in stellar cores and scattered by supernova explosions and planetary nebulae. Each generation of stars was born from gas slightly richer than the last, and over billions of years, the galaxy's chemical composition transformed. This transformation enabled complexity. Early stars could only form from hydrogen and helium, limiting the kinds of structures they could create. But later generations, born from enriched gas, could form rocky planets, atmospheres rich in oxygen and nitrogen, and molecules capable of supporting life. The impact of stellar death was cumulative, building up the raw materials for everything we see today. Earth itself is a product of this process, formed from gas and dust enriched by countless earlier generations of stars. Without the echoes of those ancient deaths, our planet could not exist. The impact also shaped the structure of the galaxy. Supernova explosions do not just enrich gas, they also heat it and push it around. Over time, the energy from countless explosions has created large-scale structures, bubbles and chimneys of hot gas that extend above and below the galactic disk. These structures allow gas to escape from the disk into the halo, reducing the amount available for star formation. The impact of stellar death is therefore not just additive but regulatory, controlling how quickly the galaxy forms stars and how its structure evolves. The timing of stellar deaths has also left marks. In the early history of the galaxy, when star formation was rapid, supernovae were frequent. The impact was intense, with shock waves crisscrossing the galaxy, enriching the gas quickly and triggering bursts of new star formation. As the galaxy aged and the rate of star formation declined, the frequency of supernovae dropped. The impact became more measured, less dramatic, but still persistent. The galaxy's history is therefore written in the cadence of stellar deaths, with periods of intense activity followed by quieter eras. Astronomers can read this history by studying the chemical composition of stars. Old stars in the galactic halo have low levels of heavy elements, reflecting their formation in the early, less enriched galaxy. Younger stars near the Sun have much higher levels, showing the cumulative impact of billions of years of stellar death. By analysing these compositions, astronomers can trace the galaxy's enrichment history, seeing how the abundance of elements changed over time and how different regions evolved at different rates. The impact extends to the formation of planetary systems. The presence of heavy elements in the gas from which stars form affects the properties of the planets that accompany them. Systems rich in metals, in the astronomical sense of elements, heavier than helium, are more likely to form rocky planets. Systems poor in metals may form only gas giants, or no planets at all. The impact of stellar death, therefore, influences not just the existence of planets, but their diversity, their compositions, and their potential to support life. Life itself is an echo of stellar death. Every living organism on Earth is made of atoms forged in stars. The carbon that forms the backbone of organic molecules, the oxygen that we breathe, the phosphorus in DNA, the calcium in bones, all came from stars that died before the Sun was born. The impact of those deaths is not abstract but immediate, present in every cell, every breath, every heartbeat. We are not separate from the graveyard but products of it, echoes of ancient explosions that travelled across space and time to become us. The impact also extends to the future. As more stars die, the galaxy will continue to change. The gas will become more enriched, star formation will slow, and the population will shift toward older, dimmer stars. Eventually, the Milky Way will merge with the Andromeda Galaxy, a collision that will trigger a final burst of star formation, followed by a long decline. The impact of stellar deaths occurring today will shape that future, determining how much gas remains, how many new stars can form, and what the merged galaxy will look like billions of years from now. There are also impacts on the cosmic scale. The heavy elements produced by stellar deaths are not confined to the Milky Way. When galaxies collide, they exchange gas, spreading enriched material across intergalactic space. Supernova explosions in smaller galaxies can eject gas entirely, carrying heavy elements into the voids between galaxies. Over cosmic time, the impact of stellar death has enriched not just individual galaxies, but the universe as a whole, ensuring that even the most isolated regions contain traces of earlier generations of stars. The echoes through time are, therefore, layered, interconnected, and pervasive. They are written in the spectra of stars, the chemistry of planets, the structure of galaxies, and the biology of life. The impact of galactic graveyards is not confined to the past, but extends into the present and the future, shaping everything we observe and everything that will come. The graveyard is not a static place, but a dynamic force, an engine of change that has been operating for billions of years and will continue for billions more. Understanding this impact changes how we see ourselves. We are not isolated beings on a single planet, but participants in a cosmic story that stretches across the galaxy and across time. The atoms in our bodies carry the echoes of ancient stars. The air we breathe is a product of their deaths. The ground beneath our feet is made from their remnants. The impact of galactic graveyards is personal, immediate, and profound, connecting us to the deep history of the universe. Behind every discovery about galactic graveyards, behind every spectrum analysed and every remnant mapped, are people. Astronomers, physicists, engineers, and thinkers who dedicated their lives to understanding what happens when stars die. These are the dreamers. The individuals who looked up at the night sky and wondered not just what they were seeing, but what it meant. Their stories are woven into the story of the graveyard itself, and their curiosity, persistence, and creativity shaped how humanity came to understand stellar death. Subramanian Chandrasekhar was one such dreamer. Born in India in 1910, he became fascinated by stars and physics at a young age. While travelling by ship to England as a graduate student, He calculated what would happen to a star after it exhausted its fuel. His conclusion was startling. There was a maximum mass beyond which a star could not remain a white dwarf. It would collapse further, into something even denser. When he presented his findings, he faced skepticism from established scientists, including Arthur Eddington, who dismissed the idea. But Chandrasekhar did not give up. He continued refining his work, and over time, his calculations were vindicated. The Chandrasekhar limit became a cornerstone of stellar astrophysics, and he later won the Nobel Prize. His story is one of persistence, of trusting mathematics even when others doubted. Jocelyn Bell Burnell represents another kind of dreamer. As a graduate student in the 1960s, she was responsible for analysing data from a new radio telescope. The task was tedious, scanning charts for signals. But she noticed something unusual. Regular pulses of radio waves appearing with extraordinary precision. She brought the discovery to her supervisor, Anthony Hewish, and together they confirmed that the signals were real. At first, the regularity was so striking that they jokingly considered the possibility of extraterrestrial signals. But further analysis revealed the true explanation: rapidly spinning neutron stars. The discovery of pulsars was a breakthrough, confirming decades-old predictions and opening a new field of study. Bell Burnell did not receive the Nobel Prize for the discovery, a decision that remains controversial, but her contribution is undeniable. Her story is one of careful observation, of noticing what others might have overlooked. Fritz Zwicky was a dreamer of a different sort. Brilliant, eccentric, and often difficult, he made bold predictions that others found hard to believe. In the 1930s, he proposed that supernovae were not just bright stars but the explosive deaths of massive stars, and that they would leave behind neutron stars. At the time, neutrons had only just been discovered, and the idea of a star made entirely of them seemed absurd. Zwicky's personality made it easy for others to dismiss his ideas, and he was often marginalized by the scientific community. But decades later, when pulsars were discovered, his predictions were confirmed. His story is one of vision, of seeing possibilities before the evidence was there, even at the cost of being isolated. Vera Rubin, though best known for her work on dark matter, also contributed to understanding the galaxy's structure and the distribution of stellar populations. Her careful measurements of how stars moved in galaxies revealed patterns that challenged existing models. She worked at a time when women in astronomy faced significant barriers, but she persisted, making observations that reshaped the field. Her story, like those of many other women in science, is one of overcoming obstacles, of insisting on being heard, and of contributing essential knowledge despite systemic resistance. The development of gravitational wave astronomy brought new dreamers into the story. Rainer Weiss, Kip Thorne, and Barry Barish led the effort to build LIGO, the Laser Interferometer Gravitational Wave Observatory. The project spanned decades, required extraordinary precision, and faced skepticism about whether gravitational waves could ever be detected. But in 2015, the detectors captured the signal of two black holes merging, a discovery that confirmed Einstein's predictions and opened a new way of observing the universe. Their story is one of long-term commitment, of building instruments that push technology to its limits, and of patience in waiting for the universe to reveal itself. There are also countless lesser-known dreamers, the graduate students who spent years analysing data, the engineers who designed and built telescopes, the software developers who wrote code to process observations. Each contributed to the collective effort of mapping the graveyard. Their names may not be famous, but their work is essential. Science is not built by individuals alone, but by communities, by the accumulated efforts of many people working toward shared goals. The human element also includes those who were wrong, scientists who proposed theories that were later disproven, who made mistakes in their calculations, or who resisted new ideas. These too are part of the story, because science advances through error as much as through success. Mistakes reveal what does not work, guiding others toward what does. The history of galactic graveyards is filled with false starts, revised theories, and abandoned ideas. all necessary steps in the process of discovery. What unites these dreamers is curiosity. They looked at the sky and asked questions. What are stars made of? What happens when they die? What do their remnants tell us? They pursued those questions not for fame or fortune, though some achieved both, but because they wanted to know. The graveyard is not just a physical place, but a testament to human curiosity, to the desire to understand the universe and our place in it. The dreamers also faced personal challenges. Some struggled with health, others with poverty, still others with discrimination. Yet they persisted, driven by something deeper than comfort or convenience. Their stories remind us that knowledge is not handed down but earned, built through effort, sacrifice, and the willingness to keep going even when the path is difficult. Today, new dreamers continue the work. Astronomers use the James Webb Space Telescope to study the remnants of the earlier stars. Gravitational wave detectors listen for mergers across the universe. Computer simulations model the deaths of stars in ever greater detail. The investigation of galactic graveyards is ongoing, and each new generation brings fresh perspectives, new tools, and new questions. The human element is not confined to the past, but extends into the present and the future. In studying the graveyard, we honour the dreamers who made it possible. Their insights, their persistence, and their curiosity are part of the story. The remnants of stars are archives of cosmic history, but the story of how we learn to read those archives is equally important. It is a human story, filled with creativity, struggle, and the quiet determination to understand what lies beyond our world. The path to understanding galactic graveyards was not smooth. At almost every step, new ideas faced resistance. Scientists doubted that stars could die, that white dwarfs could be so dense, that neutron stars could exist, that black holes were real. The opposition was not driven by malice, but by caution, by the need to test extraordinary claims with extraordinary evidence. The battle for truth was fought in papers, conferences, and observations, a slow process of convincing skeptics and overcoming the inertia of established ideas. This opposition, though frustrating for those proposing new theories, was ultimately essential. It ensured that only ideas supported by evidence survived. The resistance to stellar death began with philosophy. For centuries, the heavens were thought to be perfect and unchanging. Aristotle's cosmology, which dominated Western thought for over 1,000 years, held that everything beyond the moon was eternal. The observation of novas and supernovas challenged this view, but the challenge was not easily accepted. Tycho Brahe's supernova of 1572 provided clear evidence of change in the heavens, yet many clung to the old ideas, proposing alternative explanations that preserved the notion of celestial perfection. The battle was not just scientific but philosophical, a clash between competing worldviews. When white dwarfs were discovered, the opposition took a different form. The densities required to explain observations of stars like Sirius B seemed impossible. Some scientists proposed that the measurements were wrong, that the spectra had been misinterpreted, or that some unknown process was at work. Arthur Eddington, one of the leading astronomers of the early 20th century, famously resisted Chandrasekhar's calculations, arguing that nature would not allow such extreme collapses. Eddington's opposition, which was based not on ignorance, but on discomfort with the implications. If stars could collapse beyond white dwarfs, what other extremes might exist? The resistance was a way of maintaining control over an increasingly strange universe. The prediction of neutron stars met with even greater skepticism. When Fritz Zwicky and Walter Bade proposed in the 1930s that supernovae might leave behind cores made entirely of neutrons, most scientists dismissed the idea. Neutrons had only recently been discovered, and the notion of a star made of them seemed far-fetched. For decades, neutron stars remained a theoretical curiosity, mentioned in a few papers but largely ignored. The opposition was not vocal but passive, a lack of interest that delayed progress. It was only with the discovery of pulsars in 1967 that neutron stars became impossible to ignore. Black holes faced the strongest and longest opposition. Even Einstein, whose theory of general relativity predicted their existence, was uncomfortable with the idea. He published a paper in 1939 arguing that singularities could not form in nature. Other physicists shared his discomfort, proposing modifications to the theory that would prevent collapses. The opposition was rooted in the implications. If black holes existed, they represented a breakdown of physics, a place where the laws stopped working. For many, this was too unsettling to accept. Better to assume they did not exist than to face the consequences. The battle for black holes was fought on multiple fronts. Theorists debated the mathematics, searching for loopholes or alternative interpretations. Observers looked for evidence, but detecting an invisible object is extraordinarily difficult. The breakthrough came with X-ray astronomy. In the 1970s, satellites detected intense X-ray emissions from binary systems where matter spiraled into unseen companions. The properties of these systems, the masses, the dynamics, matched the predictions for black holes. Slowly, the opposition crumbled. By the late 20th century, the existence of black holes was widely accepted, though some questions remained. Even with acceptance, new forms of opposition emerged. Some scientists questioned whether black holes truly had singularities or whether quantum effects might intervene. Others debated the information paradox, whether information falling into a black hole was lost forever or preserved in some form. These debates were not about whether black holes existed, but about their deeper nature. The battle for truth shifted from existence to understanding, from whether to how. The opposition also appeared in the interpretation of data. When gravitational waves were first detected in 2015, some scientists questioned the analysis, suggesting that the signal might be noise or an artifact of the detectors. The LIGO team had anticipated this, and had designed rigorous tests to rule out false positives. The evidence was overwhelming, and the opposition quickly faded. But the episode highlighted how even in the 21st century, extraordinary claims require extraordinary scrutiny. The resistance to new ideas is not a flaw in science, but a feature. It ensures that theories are tested, that evidence is examined carefully, and that conclusions are robust. The battle for truth is slow and often frustrating, but it produces knowledge that is reliable. The opposition to stellar death, to white dwarfs, to neutron stars, and to black holes was ultimately overcome because the evidence was compelling. But the process took decades, sometimes generations, and required patience, persistence, and the willingness to keep presenting the evidence until skeptics were convinced. There is also a social dimension to the opposition. New ideas often threaten established hierarchies. Junior scientists proposing radical theories face resistance from senior figures whose careers are built on older models. Women and scientists from marginalized backgrounds face additional barriers, their ideas dismissed or ignored more readily than those from privileged groups. The battle for truth is not just intellectual but social, shaped by power dynamics and biases. Recognizing this helps us understand why some ideas took so long to be accepted and why some voices were silenced or overlooked. The opposition to galactic graveyards was therefore multifaceted. It was philosophical, rooted in older worldviews. It was scientific, demanding rigorous evidence. It was social, shaped by hierarchies and biases. But ultimately, the evidence won. The graveyard revealed itself through observations. Through the detection of white dwarfs, pulsars, black holes, and supernova remnants. The battle for truth was long, but truth prevailed, not because it was easy, but because it was supported by reality. The opposition was overcome, and the understanding of stellar death became one of the great achievements of 20th century science. There comes a point in the study of any profound subject when the accumulation of knowledge transforms into something deeper, when facts and observations coalesce into understanding, and understanding becomes awareness. For galactic graveyards, that awakening happened gradually as astronomers, and eventually, the broader public, began to see the connections between stellar death and their own existence. It was not just that stars died and left remnants. It was that those remnants were intimately connected to everything else, to the formation of planets, to the chemistry of life, to the future of the galaxy, and to the very atoms that make up human bodies. This new awareness changed the graveyard from a distant astronomical concept into something personal and profound. The awakening began with the realization that we are made of stardust. The phrase had been used before, poetically and metaphorically, but as the science of stellar nucleosynthesis developed, it became literal. Every atom in the human body, heavier than hydrogen and helium, was forged in a star. The carbon that forms the backbone of DNA, the oxygen in water, the calcium in bones, the iron in blood, all came from stars that lived and died billions of years ago. This was not speculation but verified fact, confirmed by decades of observation and calculation. The awareness that we are physically composed of stellar remnants transformed how people thought about their relationship to the cosmos. This awareness carried weight because it bridged the gap between the abstract and the tangible. Galactic graveyards could seem remote, events happening light years away and billions of years ago. But when you looked at your own hand and realized that the atoms in it were forged in stellar cores, the distance collapsed. The graveyard was not out there, but here, in every breath, every heartbeat, every moment of existence. The awareness made the cosmic personal, connecting the vast scales of astronomy to the immediate reality of being alive. The awakening also changed how scientists thought about life itself. For decades, the focus had been on understanding how stars worked, how they died, and what remnants they left behind. But as the connections became clearer, a new question emerged. Could life exist without stellar death? The answer was no. Rocky planets require heavy elements, atmospheres require oxygen and nitrogen, and biochemistry requires carbon, phosphorus, and other elements. All of these come from dying stars. Without the graveyard, without the scattering of elements by supernovae and planetary nebulae, the universe would be limited to hydrogen and helium. Life as we know it could not exist. The graveyard was not just a backdrop to life, but a prerequisite, an essential stage in the cosmic processes that made biology possible. This realization elevated the importance of studying stellar remnants. They were no longer just curiosities, interesting objects to catalogue and measure. They were keys to understanding the origin of everything complex in the universe. Astronomers began to see their work not just as mapping the graveyard, but as tracing the pathways that led from stellar death to planetary systems to the emergence of life. The study of white dwarfs, neutron stars, and black holes became intertwined with astrobiology, with the search for other worlds, and with the question of whether life might exist elsewhere in the galaxy. The awakening also had philosophical dimensions. If we are made of stardust, if our existence depends on the deaths of earlier generations of stars, then we are not separate from the universe but part of it. This challenged older notions of humanity as separate from nature. As observers standing outside the system, the new awareness placed humanity firmly within the cosmic cycle, participants in the same processes that governed stars and galaxies. It was a humbling realization, but also an empowering one. We were connected to the universe at the deepest level, through the very atoms of our bodies. This awareness spread beyond the scientific community. Carl Sagan, the astronomer and science communicator, played a crucial role in bringing these ideas to the public. Through his television series Cosmos and his books, he explained that we are made of star stuff, that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. The phrase resonated because it was true, because it was beautiful, and because it connected people to something larger than themselves. The awakening rippled outward, touching millions who had never looked through a telescope, but who could now see themselves as part of the cosmic story. The new awareness also changed how people thought about death, both cosmic and personal. Stellar death was not an ending but a transformation, a necessary step in the cycle that created new stars, new planets, and new possibilities. This perspective offered a different way of thinking about mortality in general. Endings were not failures but transitions, moments when one form gave way to another. The graveyard embodied this truth, showing that death and creation were inseparable, that the cycle continued, and that what seemed like loss was also contribution. For astronomers, the awakening brought a renewed sense of purpose. Studying the graveyard was not just an academic exercise, but a way of understanding the origins of everything, including themselves. Each new discovery about white dwarfs, each measurement of a neutron star's mass, each detection of a black hole merger added to the larger picture. The work was technical, often involving complex mathematics and careful analysis of data, but it was also deeply meaningful. It connected the researcher to the story of the cosmos, to the processes that had made their own existence possible. The awakening also raised new questions. If stellar death was essential for life, what did that imply about the future? As the galaxy aged and star formation slowed, would the conditions for life become rarer? If life existed elsewhere in the galaxy, was it also a product of stellar graveyards, dependent on the same cycles? These questions open new avenues of research, connecting astrophysics to philosophy, to biology, and to the search for extraterrestrial intelligence. The graveyard became a central piece in the puzzle of existence, not just for understanding the past, but for imagining the future. The new awareness was not a single moment, but a gradual process, unfolding over decades as evidence accumulated and ideas spread. But once it took hold, it was impossible to unsee. The night sky was no longer just a collection of distant lights, but a living tapestry of birth, death, and transformation. The stars were not eternal, but temporary, each one part of a cycle that stretched across billions of years. And we, standing on Earth and looking up, were part of that same cycle, made from the remnants of ancient stars, connected to the graveyard through every atom of our being. This awakening changed how humanity saw itself in the universe. We were not alone, not separate, not observers standing outside. We were participants, products of the same processes that shaped stars and galaxies. The graveyard was not a place of endings, but a place of beginnings, where death gave rise to creation, where remnants became seeds, and where the cycle continued endlessly and beautifully across the vast expanse of cosmic time. After all the observations, all the theories, all the debates and discoveries, there comes a moment when the deepest truth reveals itself. For galactic graveyards, that truth is simple yet profound. The graveyard is not separate from life, but the source of it. Death and creation are not opposites, but partners, inseparable aspects of the same cosmic cycle. Every atom of oxygen in the air, every molecule of water in the ocean, every particle of dust on Earth came from stars that died before the sun was born. The graveyard is not something distant or disconnected. It is woven into the fabric of existence itself, present in every breath, every heartbeat, every moment of life. This revelation transforms everything. It means that when we study galactic graveyards, we are not studying something external, but something internal, something that is part of us. The remnants of dead stars are not relics of the past, but foundations of the present. They are the raw materials from which planets formed, the elements that make chemistry possible, and the seeds from which life emerged. Without the graveyard, without the deaths of countless generations of stars, the universe would be simple, sterile, and incapable of producing the complexity we see around us. The deepest truth is that endings are also beginnings. When a star dies, it does not vanish. Its energy spreads outward, its matter scatters into space, and its elements enrich the interstellar medium. Within a few million years, those elements become part of new clouds of gas, new collapsing regions, new stars and planets. The cycle repeats, each generation building on the remnants of the last. The graveyard is not a final resting place, but a way station, a transition point where one form of existence gives way to another. This truth is written in the chemistry of the Earth. Geologists studying rocks can trace the origins of elements back to different types of stellar events. The iron in Earth's core came from supernovae. The carbon in limestone came from stars that shed their outer layers as planetary nebulae. The gold in jewellery came from neutron star mergers. Each element carries a history, a lineage that connects it to specific stars and specific deaths. The planet beneath our feet is an archive of the graveyard, a collection of remnants that have been recycled and reorganized into new forms. The revelation extends to biology. Living organisms are made of organic molecules, complex chains of carbon, hydrogen, oxygen, nitrogen, and other elements. These molecules depend on the availability of heavy elements, which only exist because stars died. The processes of life, metabolism, reproduction, evolution, all rely on chemistry that would be impossible without the graveyard. In a universe with only hydrogen and helium, life as we know it could not exist. The graveyard is therefore not just a source of raw materials, but a necessary condition for biology, for complexity, and for consciousness. This deepest truth also challenges how we think about mortality. In human terms, death is often seen as an ending, a loss, something to be feared or mourned. But the cosmic perspective offers a different view. Death is transformation, a process that releases what was bound and allows it to become something new. The atoms that make up a human body today were once part of other organisms, other molecules, other stars. After death, those atoms will continue, becoming part of soil, air, water, and eventually other living things. The cycle continues, just as it does in the galaxy, where stellar death feeds stellar birth. The revelation is also about interconnection. Everything in the universe is connected through shared origins. The oxygen you breathe was created in a star that exploded billions of years ago. That same explosion might have created the oxygen breathed by someone on the other side of the planet, or by a tree in a forest, or by creatures that lived millions of years ago. The graveyard connects not just stars but all of existence, weaving a web of relationships that spans space and time. We are not isolated individuals but nodes in a vast network, linked to each other and to the cosmos through the atoms we share. This interconnection extends beyond Earth. If life exists on other planets, it too depends on the graveyard. Alien biologies, no matter how different from ours, would require heavy elements, and those elements come from dying stars. The graveyard is universal, a feature of every galaxy, every corner of the cosmos. Wherever complexity exists, wherever chemistry becomes rich enough to support life, the remnants of dead stars are present. The revelation is that we are not alone in our dependence on the graveyard. It is a cosmic necessity, a shared foundation for all complex structures. The deepest truth also involves time. The atoms in your body are older than the Earth, older than the Sun, older than the solar system. They were forged in stars that died before our corner of the galaxy even formed. Those atoms have travelled through space, been incorporated into gas clouds, compressed into new stars, expelled again, and eventually gathered into the planet and the life on it. Your existence is the culmination of billions of years of cycling, of deaths and births repeated countless times. You carry within you the history of the galaxy, written in the atoms that make you. This revelation does not diminish the uniqueness of life. Instead, it elevates it. Life is rare, fragile, and dependent on a precise set of conditions, but those conditions are themselves the products of the graveyard, of the cycling of matter through generations of stars. Life is not separate from the cosmos, but an expression of it, a way that the universe organizes matter into patterns capable of growth, reproduction, and awareness. The graveyard is the stage on which this drama unfolds, the source of the materials, and the driver of the cycles. The deepest truth is therefore not a single fact, but a perspective, a way of seeing the universe as a whole. The graveyard is not an end, but a process, not a place of loss, but a place of transformation. Death and life are not opposites, but aspects of the same cycle, each necessary for the other. The remnants of stars are not relics, but seeds, not endings, but beginnings. And we, standing on Earth and looking up at the night sky, are part of this cycle. Made from its remnants, shaped by its processes, and connected to it through every atom of our being. This revelation brings with it a kind of peace. The universe is not random or meaningless. It is structured, cyclical, and generative. The graveyard is not something to fear, but something to understand. Something to appreciate as the foundation of everything we know and everything we are. The deepest truth is that we are stardust, not metaphorically, but literally, and that truth connects us to the cosmos in the most profound way possible. After absorbing the revelation, after understanding that we are made of stardust and that the graveyard is the source of life itself, there comes a moment for reflection. What does it all mean? What does it say about our place in the universe? About the nature of existence? About the significance of our brief lives on this small planet? These are not scientific questions, but philosophical ones, questions that arise naturally when the vastness of cosmic time and the intimacy of personal existence meet. The graveyard invites this reflection, offering not answers but perspectives, not certainty but wonder. One way to reflect on the meaning is to consider scale. The galaxy is immense, containing hundreds of billions of stars, many of them already dead, their remnants scattered throughout space. The timescales are equally vast, billions of years stretching from the galaxy's formation to the present. Against this backdrop, the human life seems infinitesimally small, a flicker lasting less than 100 years on a planet orbiting one unremarkable star. This comparison can feel overwhelming, even diminishing. What does one life matter in the face of such immensity? But there is another way to think about scale. The atoms in your body have travelled across the galaxy and through billions of years to become you. They have been part of stars, nebulae, gas clouds, asteroids, and oceans. They have cycled through countless forms, and now, in this moment, they are arranged in a pattern that can think, feel, wonder, and reflect. This is not diminishment, but significance. The universe, in you, has become aware of itself. The graveyard, through its remnants, has given rise to consciousness. That is not small, that is extraordinary. Another reflection concerns impermanence. Stars die, planets erode, galaxies fade. Nothing in the universe lasts forever. Even the remnants, white dwarfs, neutron stars, black holes, will eventually change or disappear over unimaginable spans of time. This impermanence is a fundamental feature of reality, and it applies to human life as well. We are born, we live, and we die, and the atoms that make us will continue without us, becoming part of other structures, other beings, other cycles. This can seem melancholy, a reminder of loss and mortality. Yet impermanence is also what makes things precious. If stars lasted forever, there would be no graveyard, no scattering of elements, no enrichment of the galaxy. Life itself depends on impermanence, on the cycle of death and renewal. The fleeting nature of existence is not a flaw but a feature, the condition that allows for change, growth, and creation. A human life, though brief, is significant precisely because it is temporary. It is a unique arrangement of atoms, a pattern that has never existed before and will never exist again. That uniqueness, that singularity, is meaningful. Reflection also touches on connection. The graveyard shows that nothing exists in isolation. Every atom, every molecule, every structure is part of a larger web of relationships. The oxygen you breathe connects you to ancient stars. The water you drink connects you to comets and asteroids. The ground you walk on connects you to the remnants of countless stellar deaths. And you connect to other people, to other living things, through the atoms you share and the cycles you participate in. The graveyard is a reminder that we are not alone, not separate, but deeply interconnected with everything around us. This interconnection extends across time. The atoms in your body were once part of stars that died before the Earth existed. They will continue long after you are gone, becoming part of future beings, future worlds, future possibilities. You are a link in a chain that stretches across billions of years, connecting the past to the future. This perspective can be comforting, a reminder that though individual lives are brief, the cycle continues, and what we are made of persists. Pondering the meaning of the graveyard also raises questions about purpose. Do stars have a purpose? Do their deaths serve a function? Or are they simply the inevitable outcomes of physical processes? From a scientific perspective, there is no purpose in the teleological sense. Stars do not die in order to enrich the galaxy. They die because the laws of physics govern their evolution. But from a broader perspective, we can see that their deaths have consequences, effects that ripple outward and create new possibilities. In that sense, stellar death is generative, even if not purposeful. The same question applies to human life. Do we have a purpose? Or are we simply products of physical and biological processes? The graveyard does not answer this question, but it offers context. We are part of a cycle, participants in processes that stretch far beyond us. What we do with our lives, how we treat each other, what we create and what we leave behind, these are choices we make within the context of that larger cycle. Perhaps purpose is not something given, but something we create. Not something inherent, but something we bring into existence through our actions and our awareness. Reflection on the graveyard also invites humility. The universe is vast, ancient, and indifferent to human concerns. It does not care whether we understand it, whether we survive, or whether we flourish. The graveyard will continue long after humanity is gone, the cycles repeating, the remnants accumulating, the galaxy evolving. This indifference can seem harsh, but it can also be liberating. We are not the center of the universe, not the purpose of creation, but that does not diminish our value. It simply places us within a larger context, one where we can find meaning not through cosmic importance, but through our connections, our awareness, and our choices. Finally, reflection on the graveyard brings us back to wonder. Despite all the knowledge accumulated, all the observations made, all the theories developed, the universe remains mysterious. We know how stars die, but we do not know why the laws of physics are what they are. We know that we are made of stardust, but we do not know why the universe is capable of producing conscious beings. The graveyard answers many questions, but it also opens new ones, deeper and more profound. And perhaps that is the ultimate meaning, not to arrive at final answers, but to continue asking, to continue wondering, to continue exploring the mystery. Pondering the meaning of galactic graveyards is therefore not about finding conclusions, but about sitting with questions, about allowing the vastness of the cosmos to shape how we see ourselves and our lives. The graveyard is a mirror, reflecting back not just the physical processes of the universe, but the deeper patterns of existence, cycles, connections, impermanence, and transformation. And in that reflection, we find not certainty but perspective, not answers but wonder, not isolation but belonging. We have travelled far together through the galactic graveyard, from the first supernova observed by ancient astronomers to the gravitational waves detected by modern instruments, from the chemistry of stellar remnants to the atoms in our own bodies. We have explored white dwarfs cooling slowly, neutron stars spinning rapidly, black holes hiding behind event horizons, and nebulae glowing with the last breaths of dying stars. We have seen how death and creation are inseparable, how endings become beginnings, and how the graveyard is not a place of silence but a foundation for everything complex and beautiful in the universe. Now, as we come to the end of this journey, it is time to return to the present moment, to the night sky above, to the simple fact that you are here, breathing, thinking, connected to the cosmos through the very atoms that make you. The graveyard is vast, but it is not distant. It is here, in the stars you can see from your window, in the air you breathe, in the ground beneath your feet. The legacy of stellar death is written everywhere, and by understanding it, we understand ourselves more deeply. The legacy of galactic graveyards is not just chemical but structural. The galaxy itself has been shaped by billions of stellar deaths. The distribution of elements, the triggering of star formation, the regulation of gas, all are consequences of the graveyard. The Milky Way as we know it, with its spiral arms, its central black hole, its diverse stellar populations, is a product of countless cycles of birth and death. The graveyard is not a footnote to the galaxy's story, but a central chapter, one that has been written over billions of years and continues to be written today. The legacy is also biological. Life on Earth depends on the elements scattered by dying stars. Without the carbon, oxygen, nitrogen, and phosphorus produced in stellar cores and distributed by supernovae and planetary nebulae, life as we know it could not exist. The graveyard is therefore not just the history of the galaxy, but the prehistory of life, the necessary foundation that made biology possible. Every living organism, from the smallest bacterium to the largest tree to every human being, carries within it the legacy of the graveyard. This legacy extends into the future. The sun will one day join the graveyard, swelling into a red giant, shedding its outer layers and leaving behind a white dwarf. Earth will not survive in its current form, but the atoms that make it up will persist, scattered into space, becoming part of new clouds, new stars, new planets. The cycle will continue, just as it has for billions of years. The legacy of our own star will be added to the legacy of countless others, contributing to the ongoing enrichment of the galaxy. The return, then, is not a departure from the graveyard, but an acknowledgement that we live within it. When you look up at the night sky, you are looking at a mixture of living stars and remnants, of bright lights and hidden masses, of visible beauty and invisible structures. The stars you see may be young or old, nearby or distant, but all of them are part of the same cycle. Some will die in your lifetime, though you will not see it happen. Others have already died, their light still travelling toward Earth. The sky is a tapestry woven from past, present, and future, and the graveyard is the thread that connects them. Returning to the present moment means recognizing that the grand cosmic processes we have explored are not separate from daily life. The oxygen you breathe was made in a star. The calcium in your bones was forged in a supernova. The iron in your blood came from the explosion of a massive star billions of years ago. These are not metaphors but facts, connections between the vast and the intimate, between the ancient and the immediate. The graveyard is not somewhere else. It is here, now, in every breath, every heartbeat, every moment of existence. The legacy of understanding galactic graveyards is also a gift to future generations. The knowledge accumulated over the past century, the observations, the theories, the discoveries, are not ends in themselves but foundations for what comes next. Future astronomers will use new instruments to probe the graveyard more deeply, to find remnants we have not yet detected, to answer questions we have not yet asked. The study of stellar death will continue, not because it is finished, but because the universe is vast and the graveyard holds more secrets than we have yet uncovered. This legacy also shapes how we think about our place in the universe. We are not outsiders looking in, but participants in the cosmic cycle. The atoms that make us were forged in stars, scattered by death, and gathered into planets and life. We are temporary arrangements of matter, brief patterns in the long flow of cosmic time, but we are also aware, capable of understanding the processes that created us, capable of looking up at the stars and recognizing our connection to them. That awareness is part of the legacy, a way that the universe has come to know itself. The return also brings a sense of peace. The graveyard can seem somber, a reminder of endings and mortality, but it is also a reminder of continuity, of cycles that repeat, of matter that persists. Nothing is lost, only transformed. The stars that died billions of years ago are still here, in the elements they scattered, in the planets they helped form, in the life they made possible. The graveyard is not a place of absence, but a place of presence, where the past remains active in the present, and where the future is being seeded even now. As we close this journey, take a moment to return to the night sky. If you can, step outside, away from bright lights, and look up. The stars are there, some bright, some faint, some visible, some hidden. Among them are remnants, white dwarfs too dim to see, neutron stars pulsing in radio waves, black holes bending space. The graveyard is all around you, vast and quiet, ancient and persistent. And you are part of it, made from its remnants, connected to its cycles, a brief but beautiful expression of the universe's ongoing transformation. The legacy of galactic graveyards is written in light, in matter, in the chemistry of planets, and in the biology of life. It is a legacy of continuity, of cycles that stretch across billions of years, of death giving rise to creation. And the return is simply this: to recognize that we are not separate from that legacy, but part of it. To see the graveyard not as something distant, but as something intimate, and to find in that recognition a sense of connection, wonder, and peace. The stars shine on, the remnants persist, and the cycle continues. And you, breathing beneath the night sky, a part of it all.